Welcome back, everybody. In this video, we're going to talk about exponential growth and decay. Let's get started. Suppose that f of t is equal to a naught e to the kt, where a naught, that's how we say this, a subscript 0, is some positive number. This is what we call an exponential growth or decay model. Exponential coming from the fact that I've got e to the some power of my variable. Growth, if that coefficient on our variable is positive. Decay, if it is negative. Now, these models actually model all sorts of real-life phenomena, like this one. The half-life of thorium-229 is 7,340 years. So thorium-229 is a radioactive isotope, and the half-life of radioactive isotopes is how long it takes for that isotope to lose half of its radioactivity, essentially. Given that information, how long does it take for a sample to decay to 20% of its original amount? Well, let's get started. I know that this is going to follow an exponential decay model because I'm losing stuff. So my radioactivity is going to be modeled by f of t equals some constant a naught e to the k t. Now, this constant is going to end up being the initial amount, typically, and let me show you why. So, how do I use this information to fill in the pieces? Right? If I had these pieces filled in, I would just find whatever the initial amount is, and then I'd take 20% of that, set it equal, and figure out what t is. But in order to do that, I've got to fill out my model first. So, one thing I know is that it will decay to half of its original amount in 7,340 years. Remember, a naught is the initial amount. So, if I plug in its half-life, f of 7,340, that looks like a naught e to the k 7340. K times that guy. Well, that should be equal to half the original amount. Half of the original amount. So here I have an a naught that I can divide from both sides. Remember, that's just some number. I may not know its value at the moment because I'm not given how much I start with, but it's just a number at the end of the day. So I can divide it from both sides, and I'm left with e to the 7,340k equals 0.5. We learned from our last video that to get rid of that exponential, I need to take the natural log on both sides. Make a little room here. So I take the natural log on both sides. And now I can bring this guy down to get 7,340 natural log of e equals natural log of 0.5. Now, e to what power gets me e? 1. This guy is just equal to 1. This guy, we would need to use a calculator for. Oh, excuse me. That's what I missed my k. This is 7340k. Apologies. but this guy is about negative 0.6931. So, all in all, I am left with 7340K equals negative 0.6931. All I need to do is divide both sides by 7340, and that will get me that K is negative 9.4434. Now, a quick forewarning. This is where I made a lot of mistakes as a student, which is that felt like enough work, moving on. But we haven't actually solved the problem. All we've done so far is filled in a blank in our formula. This tells us more information about the model. That f of t is equal to a naught e to the negative 9.4434 t, because now we actually know the value of k. So, remember the problem was actually asking for how long it takes for it to decay to 20% of its original amount. But that value of k was necessary in order to get that information. Let's see why. Now, I don't know the time, but whatever the time happens to be, I need to know when this function is equal to 20% or 0.2 of the original amount. Notice that if we didn't know k, we would actually have two variables in this equation. So that's why solving for k first was necessary. If you find yourself in this situation in the future, don't fret. That's just an indicator that there's something else you need to do first. Okay, but now I've got an equation in one variable to solve for t. Again, a naught, I may not know the value, but it's just a number, so I can divide both sides by it, and it'll cancel on both sides. And I need to make a little bit more room here. That will leave us with e to the negative 9.4434t equals 0.2. Next step is I need to take the natural log on both sides. And I'm going to make a little bit of room here. On the left side, that lets me bring my power down. On the right side, I need to approximate that using a calculator. So I would plug in natural log of 0.2, and I get negative 1.6094. And now I know this guy, natural log of e, is just 1. So all I have left is that negative 9.4434t equals negative 1.6094. Dividing both sides tells me that t is equal to... Excuse me, I misread my calculator there. Going back up here, I do have that k is this, but times 10 to the negative 5. So, how does that affect our answer? Well then, k is actually negative 0.0000094434 t, and I'm just going to trickle that down here. that gives me a much more reasonable answer of 17,042 years with a little bit of change. Let's try another problem. This time, though, let's do an exponential growth model. Suppose you buy a house for $130,000. If it appreciates in value by 6% per year, how much is it going to be worth in a decade? Go ahead and pause the video here to see if you can try it on your own. The answer that I found was $232,000 and, The answer that I found was $232,882.60. Quite the improvement. So, how did we get this? First of all, I know my model looks like this, an exponential growth model, and I'm given the initial amount this time, $130,000. So, I can plug that into my formula. Now I have more information about the model. I know the goal is going to be to find f of 10 because I'm trying to find out how much it's worth after 10 years. But first, I have to find k in order to be able to compute that. So how do I do it? I use the one other piece of information I haven't used yet, which is it appreciates by 6% per year. So I know after 1 year, it should be 106% of its original value, right? It starts from 100, it gains 6 more percent, so 106% of its original value. That's why I've got the 1.06 here. Then I can divide both sides by 130,000, and I'm left with e to the k equals 1.06. Taking the natural log of both sides, I get that k equals 0.0583. Now that my model is complete, I can plug in 10, and that gives me this answer. In this video, we saw how to tackle some application problems involving exponential growth and decay. That's going to do it for this one. I'll catch y'all on the next one.